China just achieved a lithography breakthrough that could make the world's most advanced chip-making technology completely obsolete. While America spent billions trying to keep China a decade behind in the semiconductor race, Chinese scientists were quietly working on something that doesn't just catch up to Western technology, it leapfrogs it entirely. The chip war everyone thought was over? It just took a turn nobody saw coming. Here's how China shattered the rules of chip-making forever. The chip war nobody saw coming. You need to understand something about the semiconductor industry. It's not like other technologies where multiple companies compete on equal footing. This is a monopoly so absolute, so carefully constructed, that it makes every other industry look like child's play. There's exactly one company on Earth that can build the machines necessary to make the world's most advanced computer chips. One. ASML, a Dutch company you've probably never heard of, controls the entire future of computing. Their extreme ultraviolet lithography machines, EUV machines, are the only tools capable of etching the microscopic circuits that power everything from your smartphone to artificial intelligence systems. And each one costs $150 million. That's more than a Boeing 737 MAX aircraft. You heard that right. A single chip-making machine costs more than a commercial airliner. But here's where it gets truly unprecedented. These machines are so complex that ASML can only produce around 50 of them per year. They weigh 180 tons, require 3 Boeing 747s to ship in pieces, and need 40 freight containers just to transport all the components. Inside, they use light so precise, it can etch patterns 50,000 times thinner than a human hair, and China couldn't buy a single one. In October 2022, the United States imposed the most aggressive export restrictions in modern history. The rules were simple and devastating. No American technology, no American parts, no American expertise could be used to help China manufacture advanced semiconductors. And since ASML's EUV machines contain critical American components, the Netherlands was pressured to ban all sales to China. Not just future sales, all sales, forever. The Western Semiconductor Alliance thought they'd just won the chip war before it even started. TSMC in Taiwan held an unshakable manufacturing advantage. ASML held the only key to advanced production. American companies like NVIDIA and AMD would dominate chip design indefinitely. China, cut off from the crown jewels of chip-making technology, would be stuck manufacturing chips that were years behind, relegated to older technology nodes, while the rest of the world raced ahead. Every expert agreed. Every government report confirmed it. China was finished in advanced semiconductors. But China wasn't playing the game everyone thought they were playing. What makes this breakthrough absolutely terrifying? While ASML celebrated their untouchable monopoly and TSMC expanded their EUV production lines, something strange was happening in Chinese research laboratories. Scientists weren't trying to reverse engineer EUV machines. They weren't attempting to build copycat versions of Western technology. They were asking a question that nobody in the West had bothered to consider. What if EUV isn't the only way? To understand why this matters, you need to know what makes modern chip-making so impossibly difficult. Computer chips are built by etching billions of transistors onto silicon wafers. The smaller the transistors, the more powerful and efficient the chip. Today's cutting-edge chips use transistors measuring just 3 nanometers. That's 3 billionths of a meter. You could fit 30,000 of them across the width of a single human hair. Creating patterns that small requires light with an incredibly short wavelength. Traditional lithography machines use deep ultraviolet light with a wavelength of 193 nanometers. But physics has a cruel limit. You can't etch patterns smaller than the wavelength of light you're using. It's like trying to paint fine details with a brush that's too thick. The details just blur together. That's why ASML's EUV machines use extreme ultraviolet light with a wavelength of just 13.5 nanometers. This light is so energetic it gets absorbed by air, by glass, by almost everything. The entire system has to operate in a perfect vacuum. The mirrors inside can't be made of normal materials. They're engineered from dozens of alternating layers, each just a few atoms thick, positioned with atomic-level precision. A single speck of dust would ruin everything. The engineering is so complex, that it took ASML 17 years and over $6 billion just to get the first EUV machine working. Even today, each machine requires over 5,000 suppliers from across the globe. No single country can build one alone. That was supposed to be China's insurmountable problem. But then came the most devastating news of all for Western chipmakers. In December 2024, researchers at the Shanghai Institute of Optics and Fine Mechanics announced they'd achieved lithography resolution, matching EUV performance using a completely different approach. Not extreme ultraviolet light, steady-state microbunching particle beam lithography. Instead of wrestling with impossibly short wavelengths of light, they're using beams of charged particles that can be focused and controlled with magnetic fields. Think about what that means. No vacuum chambers fighting against extreme ultraviolet light that gets absorbed by everything. No mirrors requiring atomic-level precision across dozens of layers. No dependence on 5,000 international suppliers. The Chinese approach uses particle accelerators technology China has been developing for decades in physics research, combined with magnetic lenses that can focus particle beams down to resolutions smaller than anything EUV can achieve. The published research showed they'd already demonstrated patterning at the 2-nanometer scale. That's beyond what current EUV machines can reliably produce. And the theoretical limits of this technology? They claim it could eventually reach resolutions below 1 nanometer. But that's not the most shocking part. The cost estimates for building these particle beam lithography systems come in at roughly 1/10 the price of an EUV machine. $15 million instead of $150 million. And because the technology relies on particle physics rather than extreme optics, China has all the domestic expertise and supply chains they need. No American components required. No Dutch suppliers that can be pressured by Washington. Complete technological independence. For the first time since the export restrictions began, Western semiconductor executives realized they might have made a catastrophic miscalculation. They didn't just fail to stop China, they may have forced China to invent something better. What happened next sent shockwaves through the entire industry. The trillion-dollar implications. The morning after China published their particle beam lithography results, ASML stock dropped 4% in a single day. That's $6 billion in market value, evaporated before lunch. But the real panic was happening behind closed doors in boardrooms across 3 continents. TSMC had just spent over $40 billion building new fabrication plants designed entirely around ASML's EUV technology. $40 billion betting on a monopoly that might not exist anymore. Their newest fab in Arizona, subsidized by $8.5 billion in American taxpayer money, uses EUV machines that could become outdated before the facility even reaches full production. Every chip they manufacture carries the cost of those $150 million machines built into the price. Now imagine you're a customer. Would you pay premium prices for TSMC chips made with the most expensive equipment on Earth? Or would you buy equally advanced chips from China made with technology that costs 1/10 as much? The implications hit like a collapsing house of cards. Samsung had invested $30 billion into EUV-based production. Intel committed over $100 billion to their own EUV roadmap. Every major chip maker in the world structured their entire future around the assumption that EUV was the only path forward. They built factories, trained engineers, established supply chains, and signed contracts, all based on ASML's irreplaceable technology. And China just made it replaceable. But this was just the beginning of the nightmare for Western tech companies. The semiconductor industry isn't just about making chips, it's about controlling the entire ecosystem. When TSMC manufactures a chip for Apple or Nvidia, they're not just providing a product, they're providing leverage, pricing power, the ability to prioritize certain customers over others, the power to shape which technologies succeed and which fail. That leverage is built entirely on scarcity, on being one of the only places on Earth that can manufacture cutting-edge semiconductors. If China can suddenly manufacture advanced chips domestically using technology that's cheaper and potentially more precise, that leverage disappears overnight. Chinese companies that were forced to buy chips from TSMC at premium prices can now source them domestically. Foreign companies that want access to the massive Chinese market might find themselves pressured to use Chinese chips instead of Taiwanese or American ones. The geopolitical implications are even more staggering. The entire Western strategy for containing China's technological rise was built on semiconductor restrictions. Advanced AI requires advanced chips. Autonomous weapon systems require advanced chips. Quantum computing, hypersonic missiles, next-generation telecommunications. Every critical technology of the 21st century runs on semiconductors. The United States spent decades constructing what they called a small yard, high fence strategy. Keep the yard small, just focus on the most critical technologies. But make the fence impossibly high. Make it so China simply cannot access the tools needed to compete in advanced semiconductors, no matter how much money or effort they invest. That fence just got bulldozed. China's particle beam lithography breakthrough doesn't just give them access to advanced chips, it gives them independence. And in geopolitics, independence is everything. They're no longer vulnerable to supply chain disruptions, no longer dependent on technology that can be sanctioned or withheld, no longer forced to play by rules written in Washington. For Musk, whose Tesla Gigafactory in Shanghai depends on stable Chinese relations, this changes everything. For Tim Cook, whose iPhone supply chain runs through China, the leverage just flipped. For Jensen Huang at NVIDIA, who generates billions from Chinese customers buying AI chips, the entire business model faces existential questions. But the stock market panic and business implications pale compared to what was happening in classified briefings across Washington. Then came the most devastating revelation of all: why the experts got it wrong. Intelligence analysts had been tracking China's semiconductor progress for years. They knew about every research lab, every published paper, every patent filing. The CIA's assessment was clear. China was at least 10 years behind in advanced lithography. The Pentagon agreed. The Commerce Department's export control strategy was built entirely on this timeline. They were all looking at the wrong metrics. Western intelligence focused on tracking China's attempts to build EUV machines. They monitored whether Chinese companies were trying to acquire ASML equipment through third parties. They watched for any signs of reverse engineering or industrial espionage targeting EUV technology. Every assessment measured China's progress by how close they were getting to replicating what the West had already built. Nobody was watching for China to build something completely different. Here's where it gets truly unprecedented. The breakthrough didn't come from a shadowy government lab working in secret. It came from the Shanghai Institute of Optics and Fine Mechanics, a research center that's been publishing openly in international journals for decades. The foundational research on steady-state microbunching technology was published in peer-reviewed papers going back to 2018. Western scientists read those papers, some even cited them. But nobody connected the dots to realize this technology could be adapted for semiconductor lithography. The Chinese researchers were hiding in plain sight. While Western chip makers assumed lithography had to be done with light, Chinese physicists were asking whether particle beams could work instead. While ASML poured billions into perfecting extreme ultraviolet optics, Shanghai researchers were adapting particle accelerator technology, originally developed for physics experiments. The genius wasn't in the secrecy, it was in the misdirection. China let the West believe they were stuck trying to catch up in the EUV race, while their best scientists were already running on a completely different track. And it wasn't just one institution. Tsinghua University had been developing advanced magnetic lens systems capable of focusing particle beams with nanometer precision. The Changchun Institute of Optics had been working on detection systems sensitive enough to map particle beam lithography in real time. The Chinese Academy of Sciences had been building compact particle accelerators far more advanced than anything Western labs were developing for lithography applications. These weren't crash programs rushed into existence after the 2022 export controls. They were long-term research initiatives that had been running for over a decade, quietly accumulating the expertise and technology needed to make particle beam lithography viable. But that's not the most shocking part. The technology might actually be superior to EUV in ways that go beyond just cost. EUV light, for all its precision, has a fundamental problem. It's photons, packets of light that scatter and diffract when they hit materials. Controlling where those photons go with perfect precision is extraordinarily difficult. That's why EUV machines need those impossibly complex mirror systems and why they can only achieve their advertised resolution under perfect conditions. Particle beams don't have that problem. Charged particles can be steered with magnetic fields with incredible precision. They don't scatter the same way photons do. They can be focused into tighter spots and controlled more accurately. In theory, particle beam lithography could achieve resolutions that EUV can never reach, no matter how much money ASML spends on development. The Chinese research papers claim their technology has already demonstrated sub-2 nanometer resolution in laboratory conditions. ASML's most advanced EUV machines, the ones that won't ship until 2026, are targeting 2 nanometer capability. China isn't catching up, they're pulling ahead. And here's where everything you thought you knew falls apart. The Western semiconductor industry assumed that advanced chip making required a massive interconnected global supply chain because that's how EUV evolved. It took 5,000 suppliers because the technology is so complex that no single country has all the expertise. But particle beam lithography is based on physics that China has been developing domestically for decades. Particle accelerators for research, magnetic focusing systems for scientific instruments, precision detection equipment for physics experiments. China didn't need to build a supply chain from scratch. They already had one, they just needed to repurpose it. The export controls didn't stop China's semiconductor ambitions, they clarified them. Before the restrictions, Chinese companies were content buying chips from TSMC and using ASML equipment when they could get it. After the restrictions, China had no choice but to develop complete technological independence, and in doing so, they stumbled onto an approach that might genuinely be better than what the West was selling. Western policymakers made a critical error. They assumed that because ASML's EUV technology was the current best solution, it was the only solution. They built an entire containment strategy around controlling one specific technology. They never considered that China might invent a better mousetrap. And it wasn't just China that was about to benefit from this miscalculation. What happens next will change everything. Within 72 hours of China's announcement, semiconductor industry analysts were already recalculating the entire global chip market. Morgan Stanley published a report warning that ASML's EUV monopoly could be structurally threatened within 5 years. Goldman Sachs downgraded TSMC's long-term outlook, citing potential disruption from alternative lithography technologies. The language was careful, diplomatic even, but the message was clear. The rules just changed. But the stock analysts were still thinking too small. China's Semiconductor Manufacturing International Corporation, SMIC, had already begun construction on a new fabrication facility in Shenzhen designed specifically for particle beam lithography, not a pilot line. Not a research facility, a full-scale commercial production fab capable of manufacturing 200,000 wafer starts per year. The groundwork had been laid months before the public announcement, which means Chinese leadership knew this breakthrough was coming and was already positioning to capitalize on it. The timeline they're targeting is staggering. First, commercial chips using particle beam lithography by late 2025, volume production by 2026. At prices 30 to 40% below equivalent chips manufactured with EUV technology. Think about what that does to the market. Apple pays TSMC over $400 per chip for the advanced processors in their highest-end devices. If Chinese manufacturers can deliver equivalent performance at $250 per chip, the pressure to switch suppliers becomes immense. And it's not just about price, it's about capacity. TSMC's advanced fabs are running at over 90% utilization. They're booked solid for years in advance. Companies that want cutting-edge chips have to wait in line, pay premium prices, and accept whatever production slots TSMC can offer them. If China suddenly adds millions of wafers of advanced chip capacity using cheaper equipment, that bottleneck breaks. The power dynamics of the entire semiconductor industry flip overnight. But China wasn't done yet. In January 2025, just weeks after the lithography announcement, The Chinese Ministry of Industry and Information Technology unveiled a $15 billion fund specifically for particle beam lithography commercialization, not research funding, commercialization. The technology was already proven. Now, they were scaling it up. The fund would support building domestic supply chains for particle accelerator components, magnetic lens systems, and precision control equipment. Everything needed to manufacture these machines at scale, entirely within China's borders. And they invited international partners. Not Western companies, they knew those would face political pressure to decline. But South Korea's Samsung was quietly approached. So was India's Tata Group, which has semiconductor ambitions. Even Japan's Canon, which had been trying unsuccessfully to compete with ASML in lithography, received overtures about licensing the technology. The message was clear. China isn't just building this for themselves. They're positioning particle beam lithography as the global alternative to ASML's monopoly. Any country tired of depending on Western-controlled semiconductor supply chains now has another option. For Musk, the implications were immediate and personal. Tesla's full self-driving computers use chips manufactured by TSMC using EUV lithography. Those chips cost Tesla roughly $1 billion per year. If Chinese manufacturers can deliver equivalent AI chips at lower prices, does Tesla stick with TSMC out of political loyalty, or do they follow the economics? And what happens to Tesla's Chinese market share if they choose wrong? The same calculation is playing out across every major tech company. Microsoft's AI servers, Amazon's cloud computing infrastructure, Google's data centers, Meta's recommendation algorithms, all running on advanced chips that could soon have cheaper Chinese alternatives. But the bigger problem wasn't lost customers for Western chipmakers. It was what China could build now that they had guaranteed access to advanced semiconductors. Chinese AI companies that had been hobbled by chip restrictions suddenly had unlimited domestic supply. Baidu, Alibaba, Tencent, all racing to develop AI systems competitive with OpenAI, and Google no longer faced the fundamental constraint of chip access. Whatever breakthroughs were happening in San Francisco could now happen simultaneously in Beijing, with no supply chain vulnerabilities. China's military modernization, which had been constrained by semiconductor bottlenecks, just got unconstrained. Advanced guidance systems, autonomous drones, AI-powered warfare platforms all require cutting-edge chips that China couldn't reliably access until now. The Pentagon's entire strategy of maintaining technological military superiority through chip control just evaporated. And it wasn't just military technology that was suddenly unlocked. China's push into renewable energy technologies, electric vehicles, advanced telecommunications, biotechnology, quantum computing, every strategic industry that requires advanced semiconductors all just became viable at a scale that wasn't possible before. The cascading effects were already visible. In February 2025, Huawei announced a new smartphone with AI capabilities that matched Apple's latest iPhone, using entirely domestically produced chips, not older technology nodes. Not compromised performance. Chips that benchmarked identically to what TSMC was producing, manufactured in China using particle beam lithography. The phone sold out in 87 minutes. Western tech companies had spent the last 3 years operating under the assumption that Chinese competitors would remain permanently hobbled by chip restrictions. Product roadmaps were built around that advantage. Investment strategies assumed it. Stock valuations priced it in, and suddenly, it was gone. But here's what nobody in the West wanted to admit publicly. This wasn't just about China catching up. In some ways, they'd moved ahead. Particle beam lithography systems are smaller and more modular than EUV machines. That means chip fabs can be built faster and cheaper. It means developing countries that could never afford ASML equipment might soon have access to advanced chip manufacturing. It means the semiconductor industry, which had been consolidating into fewer and fewer advanced manufacturers, could suddenly fragment and democratize. The monopoly that took 50 years to build just shattered. And the world that emerges from those shattered pieces won't be one where the West controls the commanding heights of technology through carefully constructed choke points. It'll be one where the chips powering your next phone, your next car, your next computer might come from anywhere. Where technological leadership isn't determined by who controls the supply chains, but by who innovates fastest. Where China isn't struggling to catch up to Western technology, they're competing head-to-head, and in some areas, racing ahead. The chip war everyone thought was over? It didn't end with Western victory through export controls. It ended with China rewriting the rules entirely. And ASML's $150 million machines, along with TSMC's decades of EUV manufacturing dominance, just became the most expensive obsolete technology in human history.